So in the last week's class, we saw how to design sequential circuits. So let's try and understand some small applications of sequential circuits in this class. We saw that how to design an ripple carry adder in one of the classes a few weeks back, where we designed an combinational full adder. So if I have to add 4 bits, so I can have 4 full adders, and we also saw that the carry will be propagated from one adder to other like this, and so you have an total delay will be 4 full adder delay, because if you have placed 4 bits out here, the carry has to come from here to here, here to, so the delay will be 4. And also if you see, there is the hardware requirement is of 4 full adders, right? So that is what how we implement an 4-bit adder with only combinational blocks. Okay, now if I have to design a 4-bit adder using sequential circuits, okay, this is how I will do out here. Now if you see here, clock is given to these two shift registers, and you have an inverted clock being given to the D flip-flop here, right? So suppose initially, let me take a starting point where I have to add x0, x1, x2, x4. This is one 4-bit data which I need to add with another 4-bit data, which is y0, y1, y2, and y3. Okay, and the net result is going to be there after adding. The net result is going to be available in this particular register, that is why it is known as accumulator. Okay, in the sequential design, this is how the microprocessors also they work in the same fashion. Okay, so this is one data, this is the second data. When I complete the addition, the final answer will be in this register. So initially I have loaded x0, x1. So during the say during the negative going edge of the clock, like the moment this is a full adder, right? So this will initially I am feeding x0 and y0. So this full adder will add x0 and y0, and the carry will be generated here, and that is being given as carry in for the next stage. Okay, so initially it will add these two, and then I have given a clock. So once the clock goes high, right, and then what happens is this is a shift register. So this data will shift here, right, from x0. It is an shift register. Shift register is we are going to move this data. So this will move, x1 will come here, y1 will come here, and because this is an flip-flop, the previous data will be returned here. So now first it will do x0 and y0, and then the carry will be available here for the next operation, since you are used an D, which acts like a delay. Now when I have the next bit x1 and y1 coming here, okay, it will and the sum, okay, now the sum is going to be it is going to come from here, and this is a shift register. So x0, when I add x0 and y0, right, the carry will be available here. A sum is going to come into this register, right? In the next clock cycle, I have x1 coming here, y1 coming here. Again, it will be added, and the previous generated carry will also be generated. The carry from x0, y0 will also be added, and the new sum in the next clock cycle, it will be pushed from here. So the initial sum will come to x3. The new sum which we got after adding x1 and y1, that will come to here like, right? So again the next bit, and with each clock this will keep shifting towards the right. So you add x1, y1, then you add x2, y2. It will come, it is being shifted towards the right with every clock, right? So x2, y2, whereas this will hold the carry from the previous clock, right? So x1, y1, whatever was the carry, plus x2, y2 it will do, and it will generate the sum. Now that will be put into the accumulator in the next clock cycle, and this will move again here. So at the end of 4 cycles, what it will do is it will add x0, x1, carry it will come here. In the next stage, x1, y1, again the carry will be added here, then x2, y2, again with the carry from the previous operation, and x3, y3 will be added here. So each time whatever happens, right, the sum which is coming here, and it is being pushed out here, right. So in 4 clock cycles, you will have the data which is being pushed out here, right. So that is how this and finally the carry will be available here. Okay, the sum will be available here, and the carry. So this is how an accumulator, within the accumulator, the data will be from the sum. It will keep coming like this. Okay. So if you want to get the carry also here, finally you have to do another shift operation to get this. You put the carry here and you give a 0 0 here. Okay, so that also can be done. So this is how. Now if you see here, the hardware requirement is pretty low, right. Only one full adder and 2 registers are used here, whereas in this case 4 full adders have been used here. So obviously there is a saving of hardware. Okay. So this is known as serial adder. Okay. And now one more application if I take, this is known as a counter based voltmeter. So I have to measure the input voltage. Okay. So the input voltage is available here, right, and this is the ramp generator. It starts from a high value and it keeps going towards low. So initially the ramp voltage will be since it is in the highest position, okay, that depends on the range. So you have to adjust the range so that this input ramp output voltage is at the highest level. So if you see here, the ramp voltage is higher than the input voltage. Okay, if the ramp voltage is, so that's why it will be 0 out here. So it is comparing these two signals out here. Okay, and slowly the ramp signal will come low, and the moment it crosses the input signal, okay, when the input signal becomes equal to the ramp voltage, a start pulse will be given to the gate. Now from the clock, the counter signal, signal is given to the counter, and the counter starts counting up. Okay, the counter will start counting up, and now when the ramp signal is also given to one more amplifier where you have grounded it out here. So when the ramp signal comes to 0 out here, a stop pulse will be given here. So this will stop counting. So the number of pulses which is passed to the counter in turn decides the final count, right. So that will be proportional to the input voltage, right. Now if you see, if the input voltage is low, right, if the input voltage is very low, then whenever the ramp voltage comes to that low voltage, only then you have this trigger start pulse coming. So number of gate clock pulses which is coming to the counter will be that much lesser, and hence the final digital count will be lesser. So the final output is in digital only. Okay. So this is how a digital voltmeter works like, right. If the input signal is very high, so the moment ramp signal comes a little bit equal to that signal, the counter will start, and since it's a high input voltage, so that much more time the gate will be open out here, and that many more pulses will be sent, and hence the counter reading will be high. So this is how we can design a counter based voltmeter. Okay, so these are all application of sequential circuits. Okay, this is the same counter based voltmeter. Again you have an amplification comparator. Okay, this is almost the same, only thing is the additional units which are shown here. From the counter you have an latch and a BCD to 7 segment decoder we will require, because this is a binary counter, right. So from the binary counter, this is okay, this is a slightly different configuration. Okay, let me explain here. You have an input signal here, you have an comparator, this is the clock generator. Okay, now in the binary counter you have some count, it will make an A to D converter. This should be this should be a D to A converter. Okay, it's written ADC, it should be. So whatever is the count, corresponding analog signal will be generated here. So the input signal, if it is more than the output signal, okay, right, then there will be a count high signal which will be given here. So the binary counter will keep going high, right? And then when both these ADC output and these two analog signals become equal, the binary counter will stop the counting. And parallelly you have an BCD counter also, right? Why it is BCD counter, we are using a parallel BCD counter is because finally you have to display the voltage, right, what is being read, that is in BCD format. So you can have a BCD counter latch and BCD to 7 segment decoder which will drive the display. So this is how our normal and voltmeters which we have in our home and labs work. Okay, so this is another version of the counter based voltmeter where we have used, and this should be a DAC, okay, a digital to analog converter. Oh, this is another and now how to measure the frequency. This is one circuit which tells us how to measure the frequency. Suppose you have an analog signal, first and foremost we need to convert it into digital. So a simple threshold, a simple inverter will convert these sinusoidal signals into rectangular pulses. So this signal has been converted into rectangular pulses. Okay, now all that we need to do is we need to enable this gate and gate for a specific duration. Okay, suppose I open this gate for 1 second, right, and I have a counter. So the number of the counter is initially 0. I am opening this gate for 1 second. So obviously the number of the final count depend when this is high, obviously these pulses will be transmitted and the counter will count high, right? So the number of pulses will be proportional to that of the frequency. If it's a low frequency, and the counter final value will be low, right? So this is, and then you can have an display. So this is an counter based frequency meter. So you can design these kind of circuits also. So and also you can use sequential circuits to drive stepper motors, right? So you have these kind of stepper motors, right? What it did is there is a permanent magnet out here, and there are 4 different coils, right? So if you find, if say for example only 2A is energized, then the magnetic field will be in the horizontal direction, and this will be the pointer or the magnet which is suspended will be in the horizontal direction, right? If only 1A is energized, it will be in the opposite direction, and similarly 2B and 2B will make this pointer to be aligned either up down or down up, right? And there could be also that you can have both these 2 coils energized, and hence in that case the resultant field will be in 45 degree, right? If both are these 2A and 2B are energized together, then this pointer or this magnet which will be this magnet will be the rotor actually, okay, the rotor of the motor, and this is the stator. So now the rotor will be aligned to say to the northwest direction. Similarly, if 1A and 2B are energized together, then this pointer will be this rotor will get aligned to the northeast direction, right? So with these 4 bits I can have 8 different positions. So these can be digital inputs. So based on this digital inputs, I can make the rotation, right? The frequency of these bits will decide the frequency of rotation, and also the actual values of these stepper motor is, you can give small variations in the digital signal. Accordingly this will go and stabilize in one position based on the digital input data. So this is one more application. So this can be from an counter or from an these inputs can be counter. So you can do up counting or down counting to get this rotor in a specific desired location. Okay, so this is how a stepper motor works like, and then we have the last circuit which we are going to discuss today is multiplier, right? So this we saw this multiplication when we read about combinational design, we saw how a multiplier can be made. So if you see here, so many full adders and half adders were used, and the delay was so how much of hardware is required, you can imagine. Okay, so this is it takes lot of chip area. So we have a simpler design. We can make a multiplier with which consumes very much lesser silicon area for that, which is known as a Booth multiplier or a sequential multiplier. So first we need to understand how this multiplication is actually done. If you see here, we are multiplying A and B. If you take A, if A, the first is 0 here, so everything we write 0 0. Again there is a 0 here, I am writing another 0 0 here, but I am shifting it towards the left and writing, okay, or I can say I am shifting this towards the right, okay. After writing 0, I am shifted this to right, okay. So instead of shifting this to left, I can say I have shifted this to right, okay, and then I am adding these two. Then what I am doing, I am taking the next bit. Now here it is 1, right? So whenever it is 1 here, I am putting the entire B out here as it is, okay, entire B, and then I am adding it, okay. After adding it, again I am shifting it towards the right and taking the next bit. So whenever A is 0, I am adding 0 0 zeros, and whenever A is 1, I am adding B. Okay, that is one thing. And after every addition, I am moving the data towards the right. Okay, so the new data, the old data, whatever is there, whatever was the result of the old data which is available, that I am moving towards the right. So this is known as sequential multiplier. So how it can be realized in an hardware is like this. Okay, I put the initial one data in this okay, these are all going to be 0 initially, this, okay. So what I want to multiply, okay, one set of data that here, right, this B, okay, which I am going to multiply, no, sorry, this is the A, okay. So that is known as the multiplier. I am putting the multiplier here and I am putting the multiplant here, okay. So initially this is all 0 here, the accumulator, this register A is 0. So if Q is 0, okay, if Q is 0, I am going to, this is a mux, right. So if Q is 0, this is the control line for the mux. If Q is 0, so I am going to, from this mux, I am going to 0 here. So 0 and 0 is going to get added out here, right. Say during the positive edge of the clock, okay, I am going to add these two data out here, and during the positive edge of the clock, that result, the addition of the result of this addition, I am going to feed into this register, okay. And during the negative edge of the clock, I am going to shift this entire data towards the right. That means this Q0, which I have already tested it once, that will get thrown out, and this entire thing will move towards the right. Now I take the next bit, okay, and if the next bit is 0, again I will add a 0 here, and the result I will add it into the accumulator during the positive edge of the clock, right. Right. So that is what it is done. Now suppose this is 1 out here, right. If this is 1 out here, in that particular case, right, instead of 0, I will add the multiplicand, okay, here, right. Whenever there is a 1 here, I am adding the multiplicand here. So this is what this particular logic is being implemented through hardware. If A is 0, I am adding 0. If one of the bit is 1 here, like in this case, then I am adding this entire B, right, and then I am also shifting it. So that is being done through this particular sequence, right. So I put the one data out here, the second data out here, I take the first bit out here, and if the first bit, if it is 0, I add a 0 itself, right. If it is 1, then I will add this particular data out here, right, and then I shift the data. So now this 0 which I have already done, I throw it out and I take the next bit out here, right, okay, and then I do the again I test for that whether it is 0 or not. If it is 0, I add 0. If it is 1, I add this entire bit out here, right. So it continues for how many our bits is there, those many cycles it will be required. So you will get the final answer which is available in this whole register together, right? This plus this, the answer will be available out here in this register after. So we'll take one example, then it will become clear to you. Okay, so let's take one example. Suppose this is initially A is all 0, so this is all 0, right? I am doing 3 into 5, so I have put in M. Here I am putting 3. Okay, so 3 and 5. This is here. I am putting 5 out here. Right? I put 3 here. I have put 5 here. This is 0 here. So first, what I am going to do is during the positive, like if you see here, this is 1, right? If this is 1, what will happen? If this is 1, okay, let me go back here. If it is 1 here, the output of the adder will be this is 0, and since it is 1 out here, a multiplicand will be added to here. That means 0 plus 1, that is available here. So during the positive edge of the clock, the value of whatever is the adder output is 0 0 1 1. Okay, so that gets loaded into the accumulator, right? This is 0, this is 3, 0 plus 3 will be 3, and that will get loaded into this register during the first positive edge of the clock. Okay, because it was 0 initially here, and it is 3 0 here, and this is 1 out here. So if it is 1, this data will get routed here, so it will, these two will get added here. So during the during the first positive edge of the clock, this value, the sum, okay, as between A and M will get entered into here. Why is that 5 bits are shown here is including this register. Okay, this is carry which is coming here. So that is why 5 is shown here. So now this gets, okay, during the negative edge of the clock, you will have a shift right operation. So you will find this one which was initially we saw, that gets thrown out, and then you have this 0, this 1, this 0, this one. So if you see, this entire thing will shift towards the right. So you have this one coming here, this one coming here, 0 0 0. So this and you have a 0 coming from this side. So this entire data gets M doesn't change, right? M is M is this, okay, between A and Q. So these are getting shifted by 1 bit. Now you have an 0 out here in the second cycle. So when the clock is going high, so this was the value of A, right? What is there in the accumulator? Since it is 0, if I go back here, it is 0. I am adding one more 0. So so whatever is the value of A, that doesn't get changed because I am adding an 0 here. So if you see here, this 0, this is not changing at all. So it is 0, same, right? This same. M remains constant throughout. So this A, since it is 0, during the positive edge of the clock, the same, it is added 0, so there is no change. Then again I do one shift right operation. So this 1 has come here, again this 1 has come here, 0. This 0 has got thrown away, so I have an end which is 1 here. Now since it is 1 here, in the next positive edge of the clock, you will have M plus A here. So these two will get added up again. You have 0 0 0 1 here, right? Okay, so this is going to remain same. Now in the negative edge of the clock, again this will get shifted towards the right. So now see, these data are getting shifted right. This one has got thrown, and in the last, since it's an 4-bit thing, this is an 4-bit multiplier which we are considering here. So I have the last load cycle in which right, this is again, since it is 0, you are not adding anything, the accumulator value remains same, and Q also remains same, and then you have do the last right operation. So if you see here, what is this answer? Final answer between A and Q will be considered as an 8-bit register. So you will have a 1 1 1 1. So that is equivalent to 15, right? So 3 into 5 becomes 15. Okay, so this is how an sequential multiplier. So if you see, the hardware is only one adder is there, and two registers, 1 mux. Whereas if you go here, you see the hardware requirement is very large. Okay, so this is how a Booth multiplier works like. You might get some questions in your final exam based on this algorithm. Some values will be given here. You will have to reproduce these kind of tables. So I can give you one more example here. So suppose I do 5 into 6. So in M I am loading a 5, that remains constant. Here it is 0, and I am putting 6 out here in Q. So it is 0 out here, right? If it is 0 here, in the next positive going, it is 0 plus 0, it will get added. So accumulator will remain the same, right? And Q is also going to remain the same. And then I have a negative going of the clutch, shift right operation. So you have this 0 being thrown out. So you have 1 0 moving here, and from the this is always an logical shift. So you will have one more 0 coming out here only. So you have 0 0. 1 1 out here, right? And now again, now it is 1 out here. So in the next positive edge of the clock, A and M gets added up. So you have 0 0 1 0 1 1 0 1, and this gets added up. So this is the value which you get now, right? That's it. And then again shift right operation. So obviously this becomes 1 0. This one comes here. Then you have 0 0. This one gets thrown out. So you have a 1 here. Now next load operation, you have 1 out here. So again with this what was there in the accumulator, this gets added up. So this plus this is this. Okay, so because it is 1 out here, so it will add these two, and you have this value out here, right? So and then again in shift right operation, right? So you have 1 0 being inserted, and this on everything getting shift towards the right. And then now this is an 0 out here. So in the last clock operation, you will this rotates because you are adding 0, so this remains same. And then you do an shift right operation, so you will have 0 0 1. Now if you see 5 into 5 into 6 is 30. Now if you see this, this is right, and 2 plus 4 6 plus 8 plus 16, so it comes out to be 30. So you get the final 30. So this is how an Booth's algorithm looks like. Okay, so thanks a lot. So we will stop it here for today.